Hello everyone, myself Ujjwal Prateek. I welcome you all to my research presentation titled Design of Variable Air Core Coupled Coaxial Solenoidal Inductors. Me and my advisor Dr. Zilko Pantich are associated with Freedom System Center at North Carolina State University. Here is the outline of today's presentation. Introduction. This paper focuses on the design of variable symmetric inductors. Variable inductors find their application in filtering, tuning, resonant circuits, wireless power transfer compensation, as well as can be used as a general laboratory prototype for various experimental purposes. Here is an example of variable inductor designed by moving a single solenoid coil from ferrite core. In this scenario, a ferrite core is fixed while a relative motion is made by moving the coil towards or further away from the core. This leads to a change in the inductance, as can be seen on this plot. This is one of the methods how variable inductance can be achieved. In literature, there are different other methods, such as DC biased inductance control as well as magnetically actuated inductors. I will discuss these methods later in my slides. As explained, one of the common ways of getting a variable inductance is by having a relative motion between an air core coil and a ferrite core. When the ferrite core is brought closer to the coil, the inductance increases, whereas when it is moved further, the inductance decreases. In a similar way, in another publication, instead of the coil, the ferrite core is moved to vary the inductance. One of the major challenges of this kind of design is that it requires a core, and the movement has to be like a physical movement, and the inductance raise is very limited. Another method used to design a variable inductor is by the use of DC biased flux on a core. This method does not require any mechanical movement and the volumetric density is very high. However, it does require a biasing circuit, and this may not be applicable for megahertz range where air core inductors are generally used. Another method found in literature is the use of magnetically actuated inductors. In this method, a polarized ferrofluid is used to control the inductance. However, it does require a complex actuation circuit to polarize the ferrofluid. Let us now look at the fixed value partially coupled symmetric inductors. These inductors are basically two solenoidal windings on the same axis. They have partial flux linkage between them. Therefore, the inductance generated is relatively higher compared to two independent windings. And the split inductor symmetry can be used in wireless power transfer circuit to reduce the potential with respect to ground. This design has some challenges, such as they are generally fixed value. It is difficult to vary the inductance once they are made. Secondly, the relative coupling is low, so the net inductance increment is not that significant. Another type of coupled inductors are air core coupled coaxial solenoidal inductors, also acronymed as ECCS. The ECCS has two sets of winding, an outer winding and an inner winding. Both the windings are connected in series, and there is a significant coupling between the two windings. This leads to a relatively higher inductance when compared with a partially coupled inductors. In the literature, ECCE's design has only been used for a fixed value. One of the major challenge with the ECCS inductor is that it requires a custom 3D design to hold the structure in place. In this research paper, we investigate the ECCS design to be applied as a variable inductor. The ECCS is analyzed for inductance variation and losses. We have selected this inductor because it has maximum coupling between the two windings, and if we can control that coupling, then we can get a very good variable inductor. Here is the table summarizing the literature survey. It can be observed that most of the solutions proposed in the literature are either tunable or symmetric. This paper proposes an inductor which can be tunable as well as symmetric at the same time. In the next section, we discuss the solenoid and ECCS inductor structure as well as a comparative analysis is presented. The inductance value of a solenoid in terms of its geometrical parameters is well known. It depends on the number of turns, radius, as well as the length of the solenoid. For an ECCS, there are two sets of winding and its inductance can be written as the sum of the self-inductance of the inner and outer windings together with the mutual inductance. Here is an equivalent circuit model of a coupled inductor which is applicable to ECCS. For the ECCS to be symmetric, the condition is that self-inductance of the inner turns must be equal to the self-inductance of the outer turns. In the literature, there is no explicit expression which describes the inductance of a ECCS with respect to the geometrical parameters. For a given inductance, outer radius, inner and outer turn gaps, together with the wire diameter, the only unknowns in the ECCS design are the number of turns. In order to get the number of turns, two expressions have been derived in paper which can be simultaneously solved. The first equation is based on the total inductance, whereas the second equation is based on the symmetry, which ensures that the self-inductance of the inner turns is equal to self-inductance of the outer turns. Once these two equations are simultaneously solved, an estimate of number of turns can be obtained, which can then be used in FEM modeling to further iterate the design and get the final numbers. In order to have a comparative analysis between a solenoid and an ECCS inductor, a optimized design is required. In this scenario, a 15-turn, 3 cm radius solenoid is optimized for maximum quality factor at 2 MHz by varying the turn gap. Litz wires are used to reduce the skin effect. Here in the plot, we can see how the quality factor varies as a function of turn gap. Initially, the quality factor increases and then decreases. The initial increase is because the proximity effect losses are reduced. However, later the inductance significantly reduces, therefore the overall quality factor decreases. In this scenario, the maximum quality factor of 1180 is obtained at turn gap of 1.85 mm, and the inductance obtained is 9.17 microhenry. Now, let's suppose if two of these inductors are used in a circuit, then that in combination can be replaced by an equivalent ECCS inductor. Our next goal is to design an optimum ECCS inductor with that value. For the nominal ECCS inductor to be designed, it is assumed that the outer dimensions of the ECCS are same as the equivalent solenoidal inductor, which is 3 cm. In this scenario, the inner radius of the ECCS is selected to be 2.5 cm, and the inner and outer turn gaps are assumed to be same. The nominal ECCS design uses the optimum turn gap obtained from the solenoidal analysis, which we found as 1.85 mm. Next, after getting these values, the number of turns are calculated using the formula derived in paper. The initial estimate is close to the final value obtained and verified in the FES simulations. After this, a misalignment based analysis is conducted to see how the parameters of an ECCS vary. As can be observed that inductance decreases with misalignment, whereas the quality factor initially increases and then slightly decreases. And it can be observed that symmetry has been maintained as the inductance of the inner turns is equivalent to the inductance of the outer turns. And it can be observed that quality factor of an ECCS is minimum at maximum alignment conditions. In the next section, we'll discuss how to design an optimal ECCS inductor. To design an optimal ECCS inductor, we have to understand that the ECCS design with highest Q at zero misalignment will be the best design. It is because the nominal design has minimum quality factor at zero misalignment. For a specified inductance value, outer and inner radius and wire diameter, the unknowns are number of turns and turn gaps. Since an ECCS is nothing but two solenoidal inductors, and we know that field outside a solenoidal inductor outside an ideal solenoidal inductor is zero, therefore the proximity effect on the outer winding due to inner winding can be neglected, and the optimal turn gap for a solenoidal inductor can be used when designing the outer turns of the ECCS inductor. In order to get the outer turns for an ECCS inductor, a simple solenoidal analysis using the FEA simulation tool can be used. For example, in this plot we can see how for different number of turns of a solenoid the optimal turn gap varies. So this curve can be used to design the outer turn gap of a ECCS. The overall process of designing the optimal ECCS inductor is essentially a parametric sweep where we increase the inner turn gap value in small steps, and for each value of the inner turn gap we use the total inductance, symmetry and optimal outer gap equations to solve simultaneously for outer turn gap, inner and outer turn values. These values are then used in FEA model to verify the design and to compensate for any non-integer solutions. And then the final values are obtained. Here we can see a flowchart which describes this process. Here is the result from the parametric analysis. As it can be observed that as the inner turn gap is increased, the quality factor of the ECCS inductor increases, and all the points shown on this plot have the same inductance and they all satisfy the equality criteria. However, the one marked in red has the maximum quality factor and be called as a optimum design. The optimum design increases the minimum quality factor obtained by nominal design by almost 20%. The parameters of the final design are mentioned in this table. In the next section, the experimental results have been presented. For experimental results, the nominal ECCS inductor is assembled using a 3D printed core and leads wire. Here you can see the 3D model of the ECCS inductor. It has the outer winding, inner winding, a sliding support and sliding slots to change the inductance, and a wing nut for locking the positions. So these allow for a stable variation of inductance. Next, we have the prototype of the nominal ECCS inductor, which was made using 3D printing and leads wire. A vector network analyzer is used to measure the inductance and quality factor by applying parallel resonance method. In this method, the inductor or the ECCS is connected in parallel with a capacitor of which the quality factor is known. And this combination is then resonated at the operating frequency, in this case 2 MHz. The data from the resonance can be used to obtain the overall quality factor. The overall quality factor together with the capacitance quality factor can be used to calculate the inductor quality factor as per this expression. As explained in the previous section, the experimental setup is shown in this figure. The VNA with two ports as well as the ECCS inductor and resonant capacitors are shown. The experiments are conducted by misaligning the inner and outer winding of the nominal ECCS inductor, and for each point the resonance is measured by changing the resonant capacitor to resonate at 2 MHz. On this plot, we can see that as the misalignment occurs, the quality factor increases and then decreases. The experimental results follow the simulation results. Similar is the profile for the inductance. And it can be observed that the simulation results are slightly below the experimental. This is because the FE analysis modeling of the leads wire has a comparatively lower quality factor than experiments. The quality factor of the capacitors used are shown here. In this case, it can be observed that quality factor is almost inversely proportional to the capacitance value. In conclusion, a compact variable ECCS inductor design has been explored. A comparative analysis has been conducted between a solenoid and ECCS inductor. It has been shown that the quality factor of the ECCS can be increased by 20% with parametric optimization. Simulations models have been developed. Experimental results are presented. The experimental results closely follow the simulation results. Here are the references used in this presentation. Thank you for listening to my presentation. I look forward to your questions. Thank you.